Hello, welcome to session number 26 in the series Microwave and Millimeter Wave Circuit Design. My name is Anurag Nigam and I'm back after a long duration. Uh, let's start with power amplifiers, and I'm going to talk about power amplifiers in general and class C amplifiers in particular, and I'm going to devote at least 2 or 3 sessions or more maybe on power amplifiers. So let's get started, right? So the topic today is going to be, and for the some of the lectures to come is going to be power amplifiers. Okay, so now why do we need them, right? Okay, so let's say we have a radio and we are doing a wireless communication. Now, power amplifiers can be used for wired communication as well as wireless communication. But for example, let's say I explain the things with respect to a wireless communication system. So let's say I have a radio for wireless communication. Now, there are two elements of this. One is going to be the RX, right? So one is going to be the RX or receiver, right? Okay, the other is going to be the TX. So the RX is going to be an antenna. So let me just draw a very quick diagram. So RX is going to be this antenna, and then it will be followed by some form of a filter, right? And then it is going to be followed by a LNA, and then it is going to be followed by a filter maybe, or a mixer, right? And a mixer has a LO, right? And then it goes to IF amplifier. So this is what a front end looks like. So a front end, RF front end basically comprises of up to LNA, right? So this is a RF front end. Okay, now here there may be another block here, rather here there may be another block. Let me just share this. Okay, so there is going to be a filter which is also called image reject filter, and then there may be a switch or a circulator here. Okay, so it can be a switch, sorry, it can be a switch, right? So switch is going to be a single pole double throw switch. Wait, okay, so there is going to be a single pole double throw switch. Let's say this is a single pole double throw switch. So one goes to the LNA side, and then this filter and an antenna is shared with the PA, right? And the PA is going to put out power this way. PA. So the RF front end basically comprises of this, right? And then this is a TX or transmitter. Correct. So basically, an antenna and a filter is shared with a switch. Okay. So when it is in a receive mode, then the switch is going to be connecting the antenna and filter to LNA. And when it is in the transmit mode, the switch will be connecting the antenna and the filter to the PA, right? So this is how it works in a TDD system, time division duplex, right? Now in a FDD system, okay, what may happen is instead of a circulator switch, there is going to be a circulator, and the circulator basically is going to be cyclic in nature, right? So if the signal comes, okay, so from the antenna, okay, so from the antenna the signal comes, it goes to LNA, right? And the when the signal comes from the PA, it goes into antenna, right? So this is what a circulator is doing in a front end. So this happens in case of a FDD system, right? So a TDD system is going to be a point to point, because in TDD system we may be having the same frequencies for transmit and receive. So that means that we do not need a relay unit in between, or a what you call an access point. or what you call uh, a base station, because it doesn't need to do a frequency translation. It always needs a switch, right? So basically you're transmitting and receiving the same band, right? Irrespective of the allocation of channels within a band, you are still transmitting and receiving the same band, right? So you don't need a base station to do a frequency translation between transmit and receive band, right? So this is what is happening in a TDD system. This is what happens mostly in the computer networks. So for example, if you talk about Wi-Fi or WiMAX or something which is related to computer networks, this is going to be a TDD system. Now in mobile networks, this is going to be a FDD system, and we are going to have a circulator rather than a switch. So we have a different transmit band and a receive band. So basically circulator is going to be good enough to do this sharing the antenna. Only thing required is that the isolation between PA and LNA has to be good, right? So there should not be anything going from PA into LNA, and so this is what is important. Okay, so now there are two kinds of system. Now without going into details, okay, let's talk about what this PA is doing in a radio or a RF front end. So RF front end comprises of switch or a circulator, LNA, PA, and a filter and an antenna, right? So this is going to be the radio front end, and what follows beyond that is going to do frequency translations, right? Up conversion or down conversion. That part is called a transceiver, right? So we are focusing on the front end, and the function of front end, okay, I can sum it up in a single statement, is going to be power translation. So what do you mean by power translation? Is when it receives a weak signal, it is supposed to amplify the power of the weak signal with the use of a LNA, right? And then when it transmits the signal, it has to put in more power into the channel so that it reaches the receiver, right? So it again up or boosts the power before it puts it into the medium, which is a wireless medium, right? So that's the role of the PA. Okay, so now the next thing, so in one statement, the function of radio front end is going to be translating the power, right? Now there are different requirements for the receive chain and the transmit chain. In receive chain, what is important is not just the power, but the power with respect to the noise, because they are almost comparable, right? So the LNA, the job of LNA is to amplify the signal same way, or ideally with the same gain as amplifying the noise, right? So the noise factor is going to be 1, right? Now if the LNA adds its own noise, right, so that is an additional cost we are paying, right? So then LNA has a noise factor which is going to be more than 1, right? So we are supposed to have very low noise factor, or in noise figure terms in dB it's going to be close to 0, right? So that's what's the design goal for LNA, which we have done in the previous section. In case of a PA, the goal is not the noise, because we are going to transmit power at a very high power level, right? So that's the goal of the PA. Now, so the PA basically has got number of specifications and number of important things, and I'm going to talk about all this. Okay, so now let's say why the PA has to put out more power. Okay, so to sum this up, okay, when signal goes through a channel, when signal goes through a channel, what happens? Okay, when signal goes through a channel A, it is going to see what is called a path loss, and previously I have talked about path loss. So it's as simple as, to understand with the analogy of a bulb. So let's say you have a bulb which emits light, right? So as you go away, that the light emitted is going to basically scatter, right? So if you have a point source like a bulb, right, so that's a bulb. Okay, so it is going to emit light equally in all the directions, right? So when this happens, then as you go away, then this power, which is basically radiated power P radiated, is going to divide by the 4 pi r square, or the total surface area. So the power density is going to shrink to P rad by 4 pi r square. Now with every point source, this drops, the power is dropping with 1 over r square, right? So as there is a distance between the transmitter and receiver, right, a distance, let's say, is r, then let's say this is a transmitter and receiver is somewhere on this surface. So there is a receiver here and this is a transmitter. So the distance r basically is going to be the cause of the loss. Basically the receiver is going to pick less power because the radiated power is divided by 4 pi r square. So that is called the path loss. Okay, that is one of the important losses, right? Then the antenna, basically this is case of a isotropic antenna, isotropic case. Okay, now let's say with the analogy of light itself, okay, instead of a bulb I'm going to use a tube light. Now I have gone from point source to a line source, so the radiation basically is going to be like this, right? If I take a cross section, or it is going to be like a donut, right? So this is like a donut, right? So basically this is going to be like a donut, right? So as you go away, the power is going to drop, but not with that rate as in a preferred direction, right? So basically there are nulls here, okay, and then the maximum radiation is along here, okay. So this is what happens with a wire as a radiator, which is a again is analogous to a tube light, right? Now so this is going to be a okay, omnidirectional antenna. So this is going to be a omnidirectional, sorry. So omnidirectional antenna is going to be like a donut. If you take a cross section, you're going to get two major lobes. One is going to be front lobe, other is going to be back lobe, right? So a tube light or a wire radiates like that, and then the power doesn't drop by r square, but it is r raised to n, which is n is less than 2, right? So this is another way of reducing path loss. The third way is, you have seen that in offices, right? In offices you will see that the lighting on the ceiling is going to be a square. Now if you do a square lighting, so you have gone from one dimension to 2 dimensions now, right? Now the radiation will look like a paperweight on that stuff. So basically again 1 by 4 pi r square, or r raised to n, the n has gone even much lower if you take a two-dimensional source. But eventually when you go away from an antenna or from a light, it becomes a point source, right? So for example, the square light would have no difference between a square light and a bulb, because both are point source if the distance is too large, right? So if the distance of a receiver is too high, then there is no difference between what you call a bulb and a square light, right? So in case of antenna, this is slightly different. We have a patch antenna, right? Or we have a patch array. Then there is going to be, so if I take a cross section of pattern, so let's say in elevation, okay, you are going to see a main lobe, and then it is going to have a certain beam width, right? And then it is going to have other side lobes. Now the idea is, so if I take an isotropic case and put the same power, okay, that is going to be less, right? Less than the power in the preferred direction or the direction of main lobe. So this is called the antenna gain. It is usually expressed as dpi, right? So if your antenna is directional, then that gain has to be accounted for, and that the gain is basically added here like this, right? So if you have a directional antenna, right, if you have a directional antenna, then you have a more radiated power in a preferred direction or direction of the main lobe, right? So the amplifier, its role is to overcome this loss due to path loss, so that the sufficient power reaches the receiver. So this is one of the roles of a PA. Second signal degradation is, let's say I have a I have a mobile phone here, right? And then there is a base station over here. Okay, so there is a base station over here. This is my mobile phone and base station. Now what happens is, in any wireless model, the signal can reach in multiple paths. It can get reflected and reach, it can have a multiple reflection, right, and then reach. So now when it reaches at different path lengths, then what's going to happen is, at some places that signal might cancel the main signal, right, at some points. Okay, so what is going to happen is, that's going to lead to fading. Okay, now the question is, if it is a stationary or a cyclostationary channel, then this fading is for a certain time duration, and the fading may go off, right? So then the various correction codes will take care of whatever you have lost, right? Or maybe you will retransmit the packet or the data packet, right? So that's how you take care of this. But then in fading also, so fading basically has to be overcome by the power level. So if you have a certain power level in the main channel, then the fading is going to be less, right? So basically the PA, the signal degradation is not only because of the path loss, but also because of fading, and this is a multipath case, right? So that is another thing. The third thing is going to be the attenuation. Okay, and this attenuation comes because of the absorption. So now you have to be careful, because this is a frequency dependent phenomena, right? So let's say we are talking about let's say H2O. Okay, H2O, or water absorption, that occurs around 22 gigahertz, right? So now we have various bands, right? You have got 1 to 2 gigahertz, that is going to be called as L band. Then S band is going to be 2 to 4 gigahertz. Then C band is going to be 4 to 8 gigahertz. Then you have got X band, which is going to be 8 to 12 gigahertz, right? And then you have got K under, or Q band, right? So that is going to be basically 12 to 18 gigahertz, right? So then there is K band, which is 18 to let's say 26 gigahertz, 18 to 20, I can put 22 gigahertz. Okay, and then you have got Ka band 22. So these boundaries, frequency boundaries, are not so sharp. Let's say 22, 26 gigahertz, and then you have U band 26 to 40 or something like that. So now let's see what's happening here. Okay, in this band you have got a maximum attenuation due to water vapor absorption, and so it is not usable. Then the nearest band which is usable is Ku band and Ka band, right? So there are many communication systems in Ka band also, right? So you are going to, your PA has to take care of the attenuation. Okay, then we go to 60 gigahertz, right? So that 60 to 68 gigahertz. Okay, somewhere in between there is going to be a oxygen absorption band, or O2 absorption band. Okay, now this is going to be used for indoor applications, because what we can do is, we want to restrict the size up to which a size of a region in which we are going to have a communication system. So this O2 absorption band is good for indoor communication, because you have a signal for indoor, and you do not want this to go outside, because other houses will use the same frequency, right? So this is advantageous, because now you can add more subscribers, or each house can have an indoor LAN kind of application, right? So you can design things in this band, right? So attenuation basically is that. Okay, now besides that, okay, there are noises, and these are the natural and the man-made noises. Okay, so it is not only a function of the PA putting out power. the power being put out has to overcome the noise when it reaches the receiver. So basically your noise should be much smaller than the signal to be able to faithfully demodulate the signal, right? So then we talk about the signal noise ratio at the receiver, right? A signal has to be stronger than the noise by a certain dB, right? Or you talk about the sensitivity of the receiver. So the output power basically depends. So P out. So one of the specifications of amplifier. So let's look at the specifications of amplifier. Okay, so one of the specifications of the amplifier is P out, or the output power, and the output power basically is decided by the 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 antenna. Okay, so that factor of antenna gain, okay, is in there, right? So basically a choice of an antenna, if it's a directional or if it is a omnidirectional, right, that would decide the power path loss, and that would decide the power which a PA has to put out. Okay, that's one thing. And then the amount of fading and fading durations for a certain channel model in a multipath system, that decides the fading, and fading decides the output power. The next thing is that what band you are transmitting. So if you are transmitting in a band adjacent to, let's say, H2O absorption, or water vapor absorption, or O2 absorption, then you are going to transmit more power for a shorter distance. So then the power budgeting will has to take into account. So P out depends on that. The third thing is the sensitivity of a receiver. So basically, let's say a maximum distance. So we have fixed a maximum distance up to which we want to transmit, R max, let's say. So then the power received at the end of R max should be stronger than the noise by certain dBs, and that basically is decided by the signal noise ratio of the detector and the gain in between. So it depends on the noise figure or of the receiver and the signal noise ratio of the detector, right? So it depends on, ultimately it depends on the sensitivity of a receiver, right? So P out basically is computed from the sensitivity of the receiver for a given communication system. So this is the specification of P out. The next thing I want to talk about is return loss. Okay, now why am I going to talk about return loss is the following. Okay, okay, why am I talking about return loss? Okay, a power amplification. So how do you amplify power? Okay, there are two ways of amplifying power. So basically power, I can assume there is going to be a voltage waveform, and then there is going to be a current waveform, correct? So this is going to be the current waveform, and this is going to be voltage waveform, right? And if I was to do this is going to be impedance, right? Now I can amplify power by having a quiescent current. Okay, so the quiescent current is just a DC value of current, and voltage swing is amplified. So basically the voltage is amplified, not the current. So this is what happens in case of a FAT device. Mostly we are using these days, let's say a PHEM device, okay, or any MOSFET. Okay, now these devices which are FETs, they are voltage controlled current source. Okay, so the quiescent current is fixed, then the voltage swing basically is the power amplification. So when you drive a MOSFET, you are driving it with the voltage, not with the current, and then depending on the quiescent current, that voltage swing in the given quiescent current, so that voltage swing in a given quiescent current is going to give you, so Vrms, Irms. Okay, so the way to amplify is you are not giving it a current gain. Okay, you are only giving it a voltage gain. So now this is the difference between the PHEM or a MOSFET kind of a device and a BJT kind of a device, because here you are only amplifying the voltage waveforms. You are not amplifying the current waveforms. They are dependent on the quiescent current, right? So you are designing in high impedance. Okay, so the output impedance is high. Okay, and the thing is, so let's say we fix the impedance to 50 ohm, right, on the load, right? The load is 50 ohm. So then voltage to current ratio is fixed now. Now you have to put out power. So you have to put out current, AC value of current also, right? So now, how do I say? There is no amplification, but what you are drawing is from the supply voltage. In case of a FET, you are drawing from a supply voltage, the current, and you are converting that current into a AC waveform, right? But that output current has no relationship with the input current, so there is no current gain. That's what I'm trying to tell you. Okay, only thing what you are going to put here is going to be a voltage gain or a voltage gain, because the gain is between input and output, right? Okay, so you are talking only about voltage gain. What you are talking about in terms of current is what the device can draw from the supply, right? So that's why when you do a device sizing for a FET, okay, then you increase the channel width, but if you keep the quiescent current down, then you are not going to get the power out of it, right? So basically it's the supply voltage which is dictating the power output and the quiescent current. So if you want to take the power up, you cannot just scale the device, right? You have to take the quiescent current up as well as the supply up, or the supply up, right? So MOSFETs or FETs are not truly a power device, right? So whenever you design amplifier using a PHEM, for example, these days PHEMs are common, then you are looking at anywhere from 20 dBm to 24 dBm P out. Now if you want to boost the, so from let's say from a 3-volt supply, okay, in case of a PHEM or MOSFET, generally you are delivering, so if you have a certain quiescent restriction, generally you can get from 20 dBm to 25 dBm. Then if you want to take power up, you take the quiescent current up, or you can increase the size to handle that quiescent current. So basically the channel width basically decides what is the maximum current a device can draw, right? So this is not a true power device. Now in case of a HBT or a BJT, okay, you can amplify the current, so you have a current gain as well as a voltage gain. So you have a current gain as well as a voltage gain, right? So now HBT is a power device, so you can drive it with the current as well as with the voltage, right? So now the restriction on the load line, or rather the output impedance which you show to a device, is much more relaxed. You can go down to a much lower impedance, right, to be delivering more power out of it. Okay, so this is what is HBT. You are going to see a current gain as well as a voltage gain. Now when it comes to impedance matching, okay, in both cases you have to match to 50 ohm, right? Okay, so now let's talk about power gains, right? So this is return loss. So the return loss, so let's say there is a PA and I put a circulator here, right? So I put in certain power and I get some reflected power. So this is a circulator, right? So this is going to be the reflected power, and this is going to be the incident power. So if I do a reflected power, sorry, divided by the incident power, this is going to be called a return loss. Now is this return loss same as S11 or if you talk in terms of scattering parameters, is that the same? The answer is no. Now let's see, I'll explain you what that is. So let's say output also is like that. Okay, so you put in a output a power, and then a power is reflected back, POR. So I would do a POR divided by PO. That is going to be the output return loss. Okay, now it can be seen the other way also, because this plane is a lossless plane, so this is going to be bilateral. So basically you can think it in terms of, if I put power into the PA, okay, then whatever is reflected back, right? So that can also be represented. So let's represent this as gamma. Okay, so I have got a gamma in, which is going to be equal to PR by PI. Now there is going to be gamma S. So if there is a power which is reflected back, okay, now what part of it is going to the load and what part of it is reflected back? So that will be called gamma S. Okay, similarly PA is putting out and a part of it is reflected back, so this is POR by PO, so that will be called gamma L. And then you are going to have a gamma out. So if I put power into, or what is reflected back, how much of that is again reflected out, so that will be called gamma out. So gamma in and gamma out are there. Now the forward gain GF, okay, is S21. So if S21 square, so because the scattering parameters are voltage ratio, so in terms of power they would be square, right? Mod of gamma L square divided by 1 minus gamma in mod of gamma n square times of 1 minus S22 times of gamma L. Okay, so this is going to be the forward gain. Now let's say gamma L is equal to 0, right? Gamma L is equal to 0, then these two terms will vanish, correct? And then let's say that gamma in is also 0, right? So this will become S21 square. Okay, so what means is that gain is same as the S21 in dB. Okay, gain in dB can be same as S21 provided it is matched at the output as well as the input, right? So you have to have a termination into 50 ohm of the PA if you are designing in a 50 ohm system, right, for having gamma L equal to 0 and gamma in equal to 0. So in that case the gain will be same as S21, and this will also be called a maximum gain. Okay, now there can be a reverse gain also, which can be S12, and same kind of a notation is there. This is going to be gamma S rather than gamma L, and this is going to be gamma out rather than this is going to be gamma out rather than gamma in, and then this is going to be S22 gamma S. Okay, right, S22 gamma S. Now in this case again the reverse gain is going to be, or reverse isolation is not going to be S12. It is S12 under a special condition that the source is 50 ohm, right? So the source is 50 ohm, so these terms are going to be 0, and then the output is matched to 50 ohm, so then only GR is equal to S12. Now let's look at the return loss, right? The return loss basically is going to be 20 log of, so input return loss is going to be 20 log of gamma in, correct? Okay, and the output return loss will be 20 log of gamma out. Is it true? Yeah. Now let's write S11, gamma in terms of S11, right? Okay, so gamma in is equal to S11 plus S12 S21 gamma L divided by 1 minus S22 times of gamma L. Okay, so now if gamma L is equal to 0, which means that this is a 50 ohm system. Okay, so the output port is terminated into 50 ohms, then gamma L equal to 0, then you have gamma in is equal to S11, right? So gamma in or return loss is S11 only when the load is terminated into 50 ohm, right? Now the next thing is gamma out. Okay, gamma out is going to be equal to S22, S12, S21, gamma S 1 minus S11 gamma S. Now gamma out is equal to S22 only when gamma S equal to 0 or the source is 50, right? Okay, so this is very clear that the return loss is not the same as S11 or S22. They are they are at the center of the Smith chart. If the thing is matched to the center of the Smith chart on both input and output, then the return loss is S11 S22. They are proportional, but they are not exact, right? So when you do a small signal, okay, you are looking at S11 S22 and you do a conjugate match, this is good enough. But when you don't do a conjugate match on input output, then the return loss should be established with respect with the use of a circulator, not with using a small signal S11 and S22. So if my point is clear, so return loss is that. Okay, the next thing I'm going to talk about is the gain. Okay, so the gain, okay, so the gain of the PA, there are usually a PA is matched conjugately on the input, and it is matched for a linearity or for efficiency, right, at the output, which may not be a conjugate match. So if you are matching for gain, that's gain is going to be the maximum gain you're going to achieve. But if you are matching, so let's put circulators here, right? So you are going to have P out, you are going to have P in here. So if I assume that the matches are absorbed into the gain, then P out by P in is called the power gain. And this is what usually a PA designer mentions as a power gain, right? Now let's say that both are conjugately matched. Okay, so this a part of this is going in, so let's say P in dash goes in, and this is going to be P reflected, and this is going to be P out dash, and this is PR dash, right? A part of it is reflected back. Okay, so P out dash divided by P in dash. That means neither of the mismatches on input output is included in the or absorbed in the gain, or rather the PA is conjugately matched on input and output, then this would be called available gain. Right, now if I usually what happens is in PA you conjugately match the input, but you match the output for a given efficiency or linearity. So in that case, this is a non-50 kind of matching to a non-50, well, matching to 50, but not exactly a conjugate match. So in that case, P out dash exists, while in case of input, P in is same as P in dash because I have conjugately matched it. So in that case, the gain is going to be P out divided by P in dash. So the output loss is included in the gain, but not the input loss. So that is called the transducer gain. Right? So these are the three types of gain. Usually a PA designer is going to mention this, but this is true because input is conjugately matched. Okay, so the next thing which comes is efficiency, and this is a very big topic in the sense that, so efficiency in the sense that PA, so we are putting out power in the receiver, in the transmitter, right? So if you look at the diagram, I'm going to put out power, and the power is going to compensate everything in the channel, right? So that it emerges at the receiver antenna much stronger than the noise, right? So when PA puts out a power, it puts it out at a certain efficiency, which is non 100%. So the maximum power in any radio is at the PA side. So the total efficiency is important because in battery operated devices, right, for example cell phones and other devices, right, the the output power has to be done at a very high efficiency, right, so that the battery life can be longer, right? So efficiency becomes important, and I have discussed efficiency trade-offs with linearity in previous sections, but now I'm going to just talk about what this efficiency numbers, how they are mentioned, and you have to do that. Okay, so if I was looking at a PA and if I have a supply VDD, so I am drawing certain DC power and I am putting certain input power and I am getting certain output power. Then if I do P out by PDC, okay, so this is going to be your drain or collector efficiency. Drain or collector efficiency. Now, if the gain is large, then P in is very small. Then this efficiency will be same as any other efficiency, right? Provided the gain is large. Now, if the gain is small, then you cannot say that drain collector efficiency is same as the other form of efficiency. What are the other forms of efficiencies? This is called power added efficiency or PAE. So what amount of power is being added? So this amount of power is being added, is it? No. Okay. Okay, so let me just make a correction. So how much power is added into a PA? Okay, that power added into a PA is that. So this will be P out divided by P in plus PDC. So this is going to be power added efficiency. So this is collector or drain efficiency. This is power added efficiency. Now if P in is small, which means that the gain is large, right? If the gain is large, then P is going to be small for a given output power. Then this efficiency will be same as the drain or collector efficiency. But if the gain is not large enough, then PA is going to be smaller than the drain or collector efficiency. Now there is another way of mentioning it. This is called conversion efficiency. Okay, and what is conversion efficiency? How much of the DC is converted to RF? Okay, so the RF which is put out is P out, and the RF which is put in is P in. So this much amount of DC was converted to RF. So this would be called a conversion efficiency. So if the gain is small, again this will be same as the drain or collector efficiency. But now you compare these two, okay, when the gain is small. Now you can be clever when you are publishing papers, but when you are working in industry you cannot be clever because the nature is not doesn't let you to be clever. Okay, so some people in publishing, they prefer this number over that number and say my efficiency is more. So usually they have to mention whether they are mentioning a power added efficiency or a conversion efficiency, right? Okay, so that's enough a note on efficiency. Then the other specification is going to be linearity. Now I want to be very clear. Various classes and their application, various class of amplifiers and their application depends on the linearity. Let me see if I'm recording. Yeah, so I'm going to stop very soon. So linearity is basically a P out should be equal to gain times of P in. This is the ideal relationship, right? Now what happens is, if this is true and you say P out is a linear function of P in, which is gain times of P in, then the gain basically is P out by P in is going to be a constant number like this, a flat gain. But what happens is, you see that as you keep increasing the input power, the output power cannot infinitely increase with the input power, because there is a limitation of the supply, and then there is a limitation of device stress and supply. Okay, so these limitations are not going to cause this to linearly increase, but then it is going to saturate, right? So in this region, what's going to happen is, this gain is going to drop like this, and this is referred to as compression, right? And if I do a single tone, or rather we have only cos of omega t, single tone, then this compression can be expressed as in dB. So let's say it compresses by 3 dB, so that's a 3 dB compression point, or 1 dB. Okay, usually in PAs we look at 1 dB compression point. Okay, so P1 dB is the output power at 1 dB minus 1 dB gain compression. Okay, but that is not all. Okay, so when you say linearity, okay, it has to be flat. Now it can also go through an expansion, right, and then a compression. That's, so it's a non-linear here itself, right? So linearity is just not so if you back off, doesn't mean that you are going into a more non-linear region. It depends on your design whether you are going into a more linear region, right, when you back off. Okay, so when you back off, you cannot just say that you back off and you are more linear. You may be non-linear depending on your design. So if you are going through a gain expansion followed by a compression, this usually happens when you are a class B amplifier, right? So now the classes come in now. So if you are a class B amplifier or a AB amplifier, then what might happen is, you will see a gain expansion, and that gain expansion is because the quiescent current ID goes up, and then you are seeing more gain. So one way to linearize is, so when this occurs, okay, I can basically take the quiescent current, reduce the quiescent current some way, okay, so that the gain can be made flat. So if you bias very low, you are going to see a gain expansion. And let's see a limiting case of the gain expansion. Let's say you have a class E amplifier. So in class E amplifier, what happens is, I'm talking about gain. So it is biased to a cutoff. Basically, there is no quiescent current. ICQ is going to be 0. And as you hit it with power, it biases up, so the gain goes up. And then it hits the saturation, and then the gain goes down. So this is what is happening with the gain in a class E amplifier. You are starting with a 0 gain, and then you are building a gain, right? So this is same as the expansion here. But in case of a class AB, this expansion is much less, right? It depends on how low you have biased. So basically you can gain efficiency numbers when you do this. When you cut out the quiescent current, you can gain higher efficiencies at this point, because at that point the quiescent current has no meaning, because when the device is RF biased, it can draw current. So if you try to switch off the PA by cutting off the quiescent current, it will not happen, okay, because the device is RF biased, right? So in a class AB amplifier, of course, when you cut the supply voltage, then the gain is going to go down to 0, and the PA basically is off, okay. But in a class E amplifiers, PA was off to start with, right? So you cannot be switched off with the quiescent current, right? So there is no question of a supply here in case of a class E amplifier, right? Rather, if it is a depletion mode, you have to pinch off the channel so that it is totally off, right? So the quiescent current has to be 0 for a class E, and the gain builds up. So this gain expansion is there, okay, which is a cause of non-linearity, okay, even when you back off. So it really depends on where you are biased, okay. So linearity is in terms of magnitude, or it can be seen like that. Now, if you are a class A amplifier, then this gain rolls off much earlier. So usually, let's say this is a AB, this is a class, rather this is a class AB or class A, then bias it as B, you are going to see expansion, okay, and then compression. So you are going to see a roll off with a class A. So this is a class A, for example, then this is more like B or AB. So you're going to see again expansion before compression. Now this is, then you would say, oh, if I want to put out more power, then I will just bias it as B or AB and then see expansion. Well, then you have to also look it in terms of phase, okay. So what happens in a class A is that when the gain is doing this, the phase is doing this. So this is phase. So this is a class A. Now in case of a class B, when the gain is doing this, the phase is just doing this, okay. So this is going to be a class B or AB, B or AB, okay. Now when you make a two stage, now you can take advantage of this. You can take advantage of this because the driver, so the driver is going to be like a class A for gain. So there is no question of efficiency over here. So you can bias it up and get the gain out of it. But with the power stage, you want efficiency. So you'll bias it like a B or AB and you can get a gain expansion. So this will be like a power stage. And the resulting is you have to balance the biasing on the matching in such a way that so let me just draw this, okay. So the resulting would be like this. So let's say a driver gain is doing this. So this is a driver gain, it just rolls off, and then the power stage gain is doing this, okay. So what is happening is the resulting is going to do this, correct. So you have gained this much of power. Now let's see in terms of phase what you have done, okay. So in case of a class A, the phase was going to do this, and the class B, A or AB, the phase was going to do this. So now you have balanced the phase also. So you have gained this excess, okay. So you can do this form of a linearization, okay. Ultimately what matters is the resultant. So if you properly bias the driver and power stage, then you can get the linearity out of it and compress much farther, okay. And this is again what happens is sometimes people just look at gain and they don't look at phase, and the driver is undersized and the phase was doing this and they were not aware of it, and they just come up with the linearity which is very bad, right. So looking at just the magnitude response of gain is not a guarantee of a linearization. You have to look at the phase response also for driver as well as power stage. So when you are a PA designer and you are designing a linear PA, which most of the systems are, communication systems are these days, then you are looking at this kind of stuff, okay. Now one more thing is I want to, because my focus is going to be class E, so one more point I want to stress here. Because the gain is going through this, and the current is going to build up like this in a class EPA. It's going to build up like this. Okay, so when the current is builds up, okay, the biasing of the device is changing. So if you have stabilized a device, okay, for if you have stabilized the device along the power, okay, so you have to be careful with the class E, because the class E may oscillate at low biasing, while it may be okay here. Now is it going to hurt you? No, in the data sheet you have to include that it has to be operated in saturation, not here, right? So for example, so this case arises in case of radars, right? So if you use a class E for a radar with a very high efficiency, it's good. But then if you say I'm going to back off the radar power level, then that's not good, right? Because in that case a class E might oscillate at low power level, or you guarantee that class E doesn't oscillate. So 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 across power stability also is important in case of a class E amplifier, right? And in case of any amplifier, across power, stability is important. Usually the instability comes under compression, okay, because you are biased and you stabilize it at under small signal. So if you stabilize it under small signal and then you do the matching, then you have made sure that when you back off the PA, it is going to be stable. But when you are designing class E, you have designed for efficiency at a given power level, which is going to be a saturated device. Then you have not made sure under small signal, because under small signal the class E is totally mismatched, right? So you should not talk about performance at a back off for a class E. Class E performance has to be at the saturation level, not at the back off level. So these are the things which you should be clear, that don't take a class E and say, okay, I want to see the back off performance, or rather I would take a class E and use under back off for linear applications. You can do that, but then the gain is way rising way steeply for the linearity numbers. You can compensate with the driver having a gain compression when the class E is going through a gain expansion, but that rate is too high for the driver to cancel it out. So getting linearity with a class E as a power stage again becomes a issue, right? So it's okay, you can use a class E as a power stage in communication system, but the back off, the driver has to compress much harder for the linearity, right? Okay, so this is the very basic, which is the qualitative basics. Now besides this, okay, there are other things which come in. Okay, now the choice of a process to do a PA, that's a very important question that books don't cover. Okay, so now what choices do we have? So I'm going to put here choice of process for a PA. And then when you talk about doing a front end and then you put a LNA along with the PA, you have to come up with a trade-off. Okay, so PHEMT device is good for LNA, but bad for PA. Okay, so this is in general. Then you have to do power combining in the PA to get the power levels up, or you have to boost up the supply voltage and the currents. So basically then that is how you take the power up. You have to increase the quiescent current and boost up the supply. So PHEMT is not good for PA, while the noise figures here are much better, because it is the device is in the bulk, then all the surface related defects are not going to be there, so the flicker noise is not going to be there. So at low frequencies, when you use PHEMT, you don't see the flicker noise which you see in the MOSFET, right? So that's what PHEMT is. Now HBT is a true power device, right? Now one more thing I want to mention with PHEMT, some enhancement mode PHEMTs, they do this kind of stuff. So this is across power performance. You pick up any enhancement mode device, this is going to do this kink, and this is going to be the cause of non-linearity. Okay, and even depletion mode also, you see this kink. When it starts compressing, it will expand and then compress. So this kink is difficult to handle in terms of linearity, right? This, I will point it out, it happens with UMS GAN process. Okay, it happens with Triquint or Corvo PHEMT process. It happens with Avago. Okay, so if you do a power stage design, you are going to see a lot of kink like this, which is difficult to balance with a driver when the power stage is doing this across power. So then the designing is difficult, right? Now HBTs basically, and another thing is there, these PHEMTs, when they compress, they tend to oscillate. So basically, if you compress this device 2 or 3 dB, they will start oscillating. So you have to make sure your stabilization is good under compression, right? So for that you might have to sacrifice something over here under small signal, right? So this is a typical. Now in case of HBTs, they compress differently, right? So because it is a power mode device, but again it depends on the power capability of the supply. Now again, there are lots of things, okay, beyond this simple device. So this device has more what you call power capability. Now the compression here can go to very large levels. Now in this case the PHEMT may even blow up, oscillate and blow up. In case of HBT, you can keep compressing it 8-9 dBs and it will not blow up, it will not oscillate. Okay, so this is the key advantage. Now going from SiGe to, or rather silicon to SiGe to GaAs to GaN. Okay, power capabilities are much larger here, much larger here, so I can use this, because here I'm going to use a HBT and here I'm going to use a PHEMT. Okay, so the power capability here is like 4 watts per mm, roughly 4 to 6 watts per mm, while the GaAs sitting at 0.7 watts or to 1 watts per mm. So that means that the layout, these devices are going to be much smaller than these devices. So for putting out power, your GaAs device MMIC is going to be much larger. HBTs, it's a different story, or BJTs is a different story. And then if you use MOSFETs, that's a different story, because MOSFET is something similar to PHEMT, but HBT is a different story here, right? The advantages, if you are having a, let's say a PHEMT process, then there are two possibilities. You have an enhancement mode and depletion mode. So if you pick up a process which has both, you can do logic circuits. Okay, while if you only have depletion mode, then you cannot do logic circuits. No logic circuits, because you don't have the complementary device. Okay, another thing is, if you have an enhancement mode, you are looking at only positive biases. Okay, but then the issue is power capability is small. But if you are using a depletion mode, you can have a higher power capability. That's why most of the PHEMs are going to be depletion mode. They are going to be higher power capability. Okay, while the biases have to be negative. So basically they have to be off chip, negative bias supplies. Okay, so negative biases you have to create, or you have to have a negative supply to create biases. So if you are using an enhancement mode, for example TriQuint process or Qorvo process, that's good, because you can do amplifiers which can be working in different power modes. Okay, because you can do logic, right? So you can have a elaborate bias supply. So Qorvo or TriQuint, or you can say Avago. I don't know what happened to this process. Okay, so that's there. When you are working in depletion mode, okay, then you have a choice of a gas or a GaN. Then you have got UMS and you have got Cree, Wolfspeed Cree. Now I'll tell you this. Here you can do PA LNAs and switches, but the problem with UMS is the linearity under backoff, okay, which they have to work on, and it's just not a model thing. Okay, while in case of Cree, the linearity is much better, but the matching is difficult. So in Cree, matching is difficult, in UMS matching is easy. Okay, UMS matching is easy, but then the linearity under backoff is a issue in UMS. With Cree, this is not. And another problem is if you are attempting a front end, for example, which has a LNA also, then UMS has a better noise figure than Cree. Cree has a very bad noise figure. Cree GaN PHEM process. So I'm talking about GaN here. So if you look at Cree GaN PHEM, its compression is very good. So for example, UMS devices compress what you call soft compression. So basically you are looking at 5-6 dB compression, while a Cree device has a much harder compression, right? And so basically you can put out more linearity with the Cree device than with the UMS. UMS basically has a certain kinky behavior under backoff, which Cree doesn't have. Again, the compression of Cree is a hard compression, while UMS has a much softer compression in GaN process. So but the problem is the LNA in Cree process is not going to be good, because its noise figures are very bad compared to UMS. So this is what the GaN is. And gas, if you took a depletion mode device, for example, if you are going to take a WIN semiconductor process, right, then you cannot do the logics, because there is no enhancement mode on WIN process, right? But if you take a Qorvo or a TriQuint process, you have enhancement as well as depletion mode device. So you'll be able to do logics, and you'll be also able to do power modes in the PA. With SiGe, you have an advantage that you have a HBT device with the MOSFET, but you can do logics along with the SiGe. But in SiGe there are distinctions. One is the IHP, other is your what is that, Global Foundries or IBM process, right? So that's an IBM process, so you call it a Global Foundry process, right? Now the frequency, or rather the frequency up to which they operate and stuff like that, so mostly it depends on the base transport factor, and or rather the base transit time. So base transit time here and base transit time here are going to differ, because this is a pentagonal germanium profile, and this one is going to be a pentagonal with retrograde on collector. Okay, so its breakdowns are much superior. Because it has a retrograde on the collector for germanium profile, while IHP doesn't have that patent. So I'm not sure if they are doing that. Another thing is that this Global Foundry is doing antimony implant in the channel. That means that the breakdown voltages can be taken up to almost like 9, 10 or 12 volts, while in IHP that's not there. Again, it's a patent thing. So this is as good as my information goes in the past. So when you pick up a SiGe process whether it is a IHP process or a global foundry process, you are going to see a lot of distinctions. Another thing is that IBM has what you call uh, shallow trench and deep trench. And in shallow trench they can do mesh. That means their inductors are as good as Q of 50 or more, while in IHP you do not have that. Okay, so these things are there. Most of the high frequency processes are going to have air bridges, and those which do not have it will not go up to high frequency. For example, as far as I know, the process which I have used, TriQuint or Qorvo, doesn't have air bridges, right? So they are I don't know about the most recent ones, right? So air bridge is there. Then how many metal layers are there? With all this, you are looking at only, like, you know what, 2 metal layer or 3 metal layer. But with silicon germanium you can have many more metal layers. Your passives are going to be much more superior in case of silicon germanium compared to that. But compared to cast, you can have a 12-inch wafer here, while you are going to have 4 to 6-inch wafer here. So production costs are going to be much lower here than over here. But then again, when you do initial prototype development, the production costs are going to be more here, because this is going to be 12 to rather 24. This is going to be a 24 mask minimum. So pre-production, what you call NRE, is going to be large on SiGe, while the production costs are going to be smaller because the wafer size is larger. Here pre-production costs are going to be smaller, but production costs are going to be much larger, right? So because the wafer is 4 to 6-inch. And then there are things with gas and GaN, right? In terms of thermal and radiation performance, again, this silicon germanium is radiation hard, while gas and GaN are not radiation hard because the substrate is conductive here. Then silicon germanium doesn't have a via to ground. Okay, that means that the back is going to be epoxied, while here in gas and GaN it is going to be soldered. So basically when you take heat out, it's easier to take heat out in gas and GaN rather than in silicon germanium, because the heat has to come out through bond wires. Now ground inductances are going to be much higher when you do silicon germanium, because you are using bond wires to establish ground. Now one option is going to be flip chip, right? But then when you do a power, those C4 bumps are going to melt at high power level. Then you have a tin protection on the C4 bumps. Okay, so that is a specialized process, costs more. Then you can have slabs, solder slabs, right, with the reinforcement of tin, right? So that's all IBM patented or Qorvo. So if you want to do power amplifiers in SiGe, you are going to choose something with a higher breakdown, which is the PA process, or kind of something like a PA process. And then you are going to also use flip chip with bumps, or rather tin and reinforced bumps. So that's what SiGe is going to be. It's going to be costlier, right? Because you have to take you have to flip the chip, right? And it's going to float when the power levels are high. Okay, with gas, no such problems. Another thing which happens in case of SiGe or silicon is the beta when you work with HBTs, especially with HBTs. Beta is a function of temperature, right? So what happens is you have to do ballasting in case of silicon germanium or silicon, which people do not talk about in gas or GaN, because this is going to be negative temperature coefficients, right? So the linearity because of temperature is going to be better in case of gas or GaN, right? So the device tends to become cooler as you hit it with more and more power, because the quiescent currents keep going down. So if I draw a typical gas or GaN, then its output characteristics are going to do this. You understand what I'm saying? So the output characteristics are going to do this, while in case of MOSFET or SiGe, they are going to do this. The beta goes up. Now what can happen is, because of negative temperature coefficients, this may do what you call ammeter collapse in case of SIGE. Okay, so there can be ammeter collapse, then that can be compensated with ballasting, and these concepts are not there in case of gas, and hardly few books cover this. Ballasting. Ballasting is, again, there are two kinds of ballasting. It can be source ballasting or a or a or rather not source, ammeter ballasting or a base ballasting. Now it depends on the bandwidth you are designing for, okay, and the matching. So really, a PA design is much more complicated than you think. It is not just taking a device and just tuning the device on the input and output and you got a PA. Okay, when you become this is a class book PA designer. When you become an industry PA designer, there are more details which you have to look into, right? When you are industry PA designer. Another thing is, let's say HBT, for example, whether I bias with the current or a voltage, then the linearities are going to be different, right? Output impedances are going to be different in two cases, and then also the ruggedness is going to be different in two cases, right? So such things are not in the books. Such things only with the experience, with the experienced people you can get it, not from the books, right? So basically, when it comes to thermal effects and all that in a PA, you have to work with a foundry. You have to have a process knowledge. It's not just you take a device and you are tuning it, and you, from an MIC engineer, you became an MMIC engineer because you could extend the tuning from a discrete device to a bare device. So that doesn't make you a PA designer, right? There are lots of things which come in when you make a PA which goes into a process. Now such things are not there in India. Such things are not taught in India. Such things are industry people are not aware of. Even after 10 years of experience, they think PA is just tuning, which is not so. Unless we have a fab, nobody would learn this kind of stuff, right? Okay, so I'm going to stop here, and later I'm going to start with the class E beyond this. Okay, thanks a lot. Thank you.